Hello everybody, I'm Francesco Maria Faticanti. I'm a PhD student from Fondazione Bruno Kessler and University of Trento, Italy. And today I will talk about our work entitled Deployment of Application Microservices in Multi-Domain Federated Fog Environments. So first of all, let me introduce the scenario where we are. We are dealing with fog computing, which is an extension of cloud computing, and this introduces a new intermediate level between the set of devices and the cloud, bringing computation and data closer to the things, so we gain a reduction of data traffic, low latency, and reduced costs, since we avoid every time to go to the cloud in order to perform some computational task that can be performed now in this new intermediate level. In this context, the paradigm of applications that better fits with this new fog computing is the microservice architecture, where application consists of multiple loosely coupled models that can be deployed along the cloud-to-thing continuum, depending on their specific requirements. For example, in this figure, we can see that we have, for example, this application that has three modules, the module A, B, and C. And for example, the first two modules, A and B, can be deployed on fog since the requirements of low latency and privacy. And the third module, C, can be deployed on the cloud since it has high computational capabilities requirements. So we are dealing with this kind of architecture for application. And also we are dealing with some additional constraints that are called locality constraints. These constraints specify the need of some microservices of a certain devices. Like, for example, in this figure, the models 1 and 2 are required to be very close to devices that are very close to some monuments like the Eiffel Tower and the Colosseum in this figure. So in this case, we have locality constraints and the usual computational requirements in terms of CPU, memory storage for each microservice, and we have networking constraints for each edge of in the application between two models. And they are characterized by bandwidth and latency requirements. So we are dealing with a federated fog scenario where we have the main fog provider, like this one showed in figure, that has not enough computational capabilities. It has not enough resources to satisfy all the application's requirements. So it has to deploy some part of the application towards external domains. But this involves some costs related to formal agreement between different fog providers, as shown in this figure. For example, in this figure, we can see that module 1 and 2 needs of a specific locality constraints because they need of some specific cameras near to monuments. And so we have to, for example, deploy the module number 2 outside the main fog provider. So this comes with a cost. And our objective in this context is to minimize the external resources usage. So first of all, we introduce a system models in order to have a formal model of our problem. And we model application like directed acyclic graphs, where each node has a CPU memory storage requirements, and each edge of application is characterized by the requirements of throughput and delay on that edge. The network infrastructure, on the other hand, is modeled through directed graph GI, where each node is a region of one provider containing a set of hosts that can host applications modules, and each edge is characterized by bandwidth and latency values. Now, in this context, the domain is modeled as a set of regions, so it's a subset of the set of vertices of our network infrastructure, and we have a cost associated to each domain. Now, given this model, we can formulate the placement problem like this. So we have an input, a set of microservices application A and a graph infrastructure GI. Our goal now is to find a feasible placement for each application that minimizes the deployment cost towards external domains, where the deployment cost is a function proportional to the number of microservices deployed on the external domains, where each domain is associated with a specific weight or cost. Under our constraints of computing, networking, and locality. Now, one typical approach of this problem is this is a static problem, so we can formulate it like an integer linear programming problem that takes in input the set of applications to be deployed and the network infrastructure graph, and it takes in input the constraints of about networking, computing, and locality, and it gives as output the placement for each application. Now, in order to provide such a formulation, we need to introduce two kinds of variables, binaries variables, one for the node mapping and one for the links mapping of the application to the infrastructure. But if we look at this formulation, we can easily see that this is a virtual network embedding problem, which is a well-known NPR problem. And also we know from theory that is hard to approximate this kind of problem. So we are looking for scalable solution which are represented by heuristic solution. So one of the most adopted method to tackle this problem is represented by a depth-first search fashion of the for the exploration of the placement space for the application into the infrastructure. More specifically, this approach deploys one application per time, and for each application, it performs the node mapping and link mapping. But this approach has some issues. In particular, given the greedy nature of this kind of approach, a depth-first exploration of the application's placement space will show some issues when you are dealing with locality constraints. In fact, for example, if some application has a common domain for their locality constraints, I mean, they are requiring the use of a specific device, of the same device on the same domain, then, and especially if that domain is has a very low cost, a greedy procedure for the application that deploys application one per time will quickly saturate all the resources of this common domain without leaving any space for other applications that have to come. So this leads to an high percentage of infeasibility for our program. So given these issues, our idea is to perform a different exploration of the application's placement space. So the idea is that once we find the topological sort of each application, so we establish an order of each modules of each application, at each step, we take all the first nodes of the topological sort and we explore the space in a breadth-first search fashion. And so at each step, we take, we consider all the nodes of each application at the same time, at each iteration. And so at each iteration, we take the first nodes of, of each application and we perform the node and links mapping. This has some benefits because with this method, we have a global view of batch deployment, and the locality constraints are better matched with this kind of approach. And as we will see in the experimental results, this will result to have a high feasibility rate. Now, if we want to have a visual scheme of these two kind of approach, we can see in this slide where we have we perform an initial topological sort of each application. For example, for the first application, we assign 0, 1, 2, 3, and 4 for to each modules. And once we perform this sorting, we explore in two different ways the space of the application placement. For example, we can see from the figure that DFS performs a visit of the space in a vertical way. So it will deploy each application per time at each iteration. Meanwhile, our approach is different because at each iteration we are considering all the modules at the same level of all the application. So consider the deployment at each step of a single component of all the applications. So we are adopting an approach that is level by level, differently from the depth first search fashion. So in order to evaluate this kind of approach, we establish some simulation settings, and we generate a network topology using the Erdős-Rényi random graph model, and we generate 6 regions and 3 domains. We set the average link bandwidth on 60 megabit per second and an average link latency of 10 milliseconds. The main fog domain in this case, we fix to have one central cloud connected to one fog region. And we evaluate our approach with different application batch sizes. Respectively, we evaluate with 10, 15, 20, 25, and 30 applications batch sizes. And in order to evaluate and to highlight the difference between the DFS and the BFS, we set the locality constraints to be the one that force each application to have the first module of each application in a specific region of the main domain, in order to see that the DFS will saturate as quickly as possible all the resources of the main domain. So in this case, we evaluate 2 variants of the DFS approach. One that we call DFS SOA no cost, that doesn't take into account the cost optimization, but it will maximize the number of deployed applications without taking into account the cost of the deployment. The second one is the variant that we presented, taking into account the cost optimization. The BFS is our proposed strategy, and the OPT is the optimal solution computed by a solver. Now, first of all, we evaluate the feasibility optimality trade-off of these solutions. Now, we can see from the first figure that the DFS cost-aware solution will saturate as quickly as possible all the domain resources, resulting in a very low percentage of feasibility as the number of applications increases. Look at the feasibility here is defined as the number of feasible instances over the total number of instances generated. Now, we can look also that the BFS and the optimal solution has the same behavior, obtaining the 100% of feasibility in all the cases. Now, on the second figure, we can see the total deployment cost for each application. Basically, we can see the average number of modules for each application that are deployed on the external domains, if we set a unit cost for each external domain. And we can see that the BFS, our proposed solution, is very close to the optimal solution. And meanwhile, the DFS cost-aware solution has a very low cost given the very low feasibility percentage showed by the first figure. Reasonably, the second variant of DFS, the one that doesn't take into account the cost, will have a high deployment cost with respect to the other solution, reasonably. but it has a very high respect to the first variant, a very high feasibility percentage. Now we can, the second thing that we want to evaluate is the resource usage of each solution that we proposed, and we investigate and we can see the bandwidth and the CPU in these two figures in the main and towards external domain. So we can see that the DFS cost-aware solution has a constant and low bandwidth consumption, given that it try to saturate as quickly as possible all the resources in the main domain, and especially it will exhaust all the resources on the specific region where we have the locality constraint. So we can see that BFS and the optimal solution has similar trend, but the optimal solution has a slightly less bandwidth consumption toward the external, reasonably, because it will deploy more applications in the main domain, since the deployment cost is slightly better in these terms. In the CPU consumption, on the other hand, we can see that the FS cost aware has also, again, low CPU consumption in the external domain, since it deploys mostly all the application inside the main domain. On the other hand, we have the DFS that doesn't take into account the cost, that has an opposite trend. In fact, we can see a higher CPU consumption toward the external domain for the second variant of the DFS. Now, another thing that we evaluate is the execution time to see the scalability of our proposed solution. We can see that our BFS has a very low execution times that is comparable to the one of the DFS no-cost solution. The DFS cost solution has a very, very low execution time given the very low feasibility percentage. So once it will find that the solution is infeasible, it finished, it's running. So they are comparable, both the BFS and the DFS no-cost solution. But we can see this figure confirms that the optimal solution is not scalable at all, since the NP hardness of the problem behind. So, in conclusion, in this talk, we presented the problem of minimized external resource usage under locality constraints in multi-domain fogs. And we show that the optimal solution is a virtual network embedding problem, which is well known to be NP hard. And so we propose algorithmic solutions that are polynomial time. And in the case of BFS solution, our proposed solution, they are very close to the optimal solution in terms of deployment cost. The takeaway message is also that the locality constraint in this context leads to think about different strategies of application deployments. So feature works. In the feature works, we want to evaluate different objective functions, like, for example, average resource consumption. And we would like to investigate a different kind of locality constraint, for example, towards external domains in experimental results. And we would like also to investigate the case where we have different weights for the cost of deploying towards the external domains. And we would like also to investigate the pricing implications of this fact. We would like also to formulate an online version of the algorithm. I would like to evaluate the distance in terms of solution, of the quality of the solution from the static strategies. And also an interesting point will be to investigate the bargaining models, in this case where microservices can be exchanged between different domains. And we would like also investigate the pricing implications of these models. So with this, I conclude my talk. Thank you for your attention, and reach out for questions. Thank you.